Hello guys, in today's video we can talk about one of the puzzling problems I had, as many of you guys could have, when I was studying circuit design. So the question is, why the DC voltage source is always considered as a short during AC analysis. Right, DC voltage source has certain voltage above the ground. Why is that one considered as a short during the analysis? Before going to explain that problem, let's first clarify that the AC analysis is always about the small signal analysis. It's about it's always about the little delta change. That delta change could be a voltage change or current change around the main bias point. So right, it's always a little change. So here let's use very common problems to explain why. So on this side, as you can see, this is here. This is a common source single stage amplifier. Right, you have certain voltage at the input, and output is here. So right now the problem is, what is the output impedance, output resistance at this node? Of course, we're talking about the small signal resistance, right, at this node. The common way we to deal with this is we apply a small signal change, or inject a small current into this node, right? So before we inject that current, right now, as you can see that the current source, this is the current source here, the value of the current source is 0. So essentially we inject nothing, right? So the voltage on this node, right, this is simulation result, is around 1.4 volts. Now, let's inject 50 nanoamps into this node. 50 nanoamps. Well, quick question. Why I inject only 50 nanoamps instead of like 5 amps, 1 amp, or even 10 microamps? Why? Think about it. That's because my bias point for this common source stage is 1 microamps only, right? Since we're talking about AC analysis, that's small signal. It's always deal with little delta change. So the signal I try to inject into this node should not be as big as this one. Usually, come practice, it's very small, a few percent, I would say. In this case, it's about 5%. So right. So after we injecting 50 nano into this node, as you can see here, the voltage on this node goes up. The DC voltage goes up by about 0.35 volts, right? It was 1.4, now it's about 1.7, 0.34. So according to the definition of the output impedance on this node, that's the change of VL voltage over the change of IL voltage, right? What is the change of VL voltage? That's the difference between this voltage and this voltage. Essentially, it's here. What's the change of IL voltage? 50 nano, right? Before it was 0, now it's 50 nano. What's the result? That's about 660 kilo ohms. So the answer is 660 kilo ohms. That's the output impedance of this node, right? Notice during the whole calculation, we never change the value of this VGS here, right? It was 435 millivolts before. Now it is, it's the same value. So the delta of VGS, the change of VGS, is 0 volts. So in the AC analysis world, we call it AC short to ground, right? This is not the true ground, but we just call it AC short because there's no change. By the way, that essentially the impedance, the output impedance of this circuit is equivalent to RL in a MOS, right, transistor. We didn't change this one, right? This delta is 0. So this one disappeared, right? It's a GM multiplied by delta VGS. That one disappeared, so we only left with this. So the RL of this MOS is 660 kilo ohms. Now, one extra question here. What is the small signal resistance of an ideal current source, right? We have an ideal current source here. What is the small signal resistance of that one? Think about it. It's actually, as you guessed, it's infinity, right? Why infinity? Just imagine if you have an ideal current source, you try to apply voltage on top of it, a delta voltage, right, on top of it. Does the current goes through this current source change? No. So, right, so delta V over 0 equal to infinity. So the resistance of the ideal current source is positive infinity. Hopefully after this video, now you can understand why the DC voltage source is considered as an AC short during the analysis. If you have an extra thought or any questions, please leave your comments below. And if you like the video, please like our videos. Give us a thumbs up. It means a lot to us. Thank you.